Lesson 122, Types of Machine Learning. Hello and welcome to Lesson 122 of our Machine Learning Foundations for Software Engineers course. In the previous lesson, we covered the essential building blocks of machine learning, features, labels, models, and the distinction between training data and new data. Today, we'll dive deeper into the three main types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. As software engineers, you're used to categorizing problems to apply the right tools and techniques. Similarly, in machine learning, we categorize problems into these three types, each with its own approaches, algorithms, and real-world applications. A solid grasp of these categories is crucial for framing ML problems correctly and selecting the appropriate methods. Let's kick things off with supervised learning, the most common type of machine learning. 1. Supervised learning. Picture this: you're tasked with building a spam email classifier. Where do you start? With supervised learning, of course. In this approach, we train models using labeled data, where the desired output is already known. So you'd begin by gathering a dataset of emails, each labeled as either spam or not spam. This labeled data serves as a teacher, guiding the model to learn the patterns that distinguish spam from legitimate emails. The key idea in supervised learning is that the model learns from examples where the correct answer is provided. It's like having a knowledgeable mentor who shows you the ropes. The model's job is to learn the mapping between input features, like the words and phrases in an email, and the corresponding output labels, spam or not spam. Supervised learning comes in two flavors. 1. Classification. This is where the model predicts a categorical label. Spam detection is a binary classification problem, spam or not spam, but classification can also be multi-class. For instance, a model that classifies images into categories like dog, cat, or bird. Other examples include sentiment analysis, positive, negative, or neutral, disease diagnosis, malignant or benign, and customer churn prediction, likely to churn or not. 2. Regression. In this case, the model predicts a continuous numeric value. A classic example is predicting housing prices based on features like square footage, number of bedrooms, location, etc. The model learns to map these input features to a specific price value. Other regression examples include predicting stock prices, estimating a patient's blood pressure, or forecasting sales revenue. Under the hood, supervised learning uses various algorithms to learn these mappings. Some popular ones include linear regression, a go-to for simple regression problems, like predicting a student's test score based on the number of hours they studied. Logistic regression, used for binary classification tasks, such as predicting whether a customer will buy a product or not. Decision trees and random forests. These algorithms shine in both classification and regression tasks. They learn hierarchical rules from the data, like if a customer is over 30 years old and has an income above $50,000, then they are likely to buy the premium product. Support vector machines, SVMs, powerful for classification tasks, especially with complex, high-dimensional data. SVMs find the optimal boundary that separates different classes. Neural networks, the superstars of supervised learning, capable of learning highly complex patterns. They're the backbone of deep learning, used in applications like image and speech recognition. The choice of algorithm depends on factors like the type of problem, classification or regression, the size and complexity of the data, and the desired interpretability of the model. 2. Unsupervised learning. Now, let's switch gears and explore unsupervised learning. In contrast to supervised learning, unsupervised learning works with unlabeled data without any predefined output or answer. It's like being dropped off in a foreign city without a map, left to explore and make sense of your surroundings on your own. The goal is to uncover hidden patterns and structures within the data. One of the most common applications of unsupervised learning is clustering. Imagine you're analyzing customer data for an e-commerce company. You have a wealth of information about customers' browsing behavior, purchase history, and demographics, but no predefined categories. Clustering algorithms can automatically group similar customers together based on their behavior and attributes. For instance, you might discover clusters like bargain hunters, loyal shoppers, and high-value customers. This insight can be invaluable for targeted marketing campaigns and personalized recommendations. Another area where unsupervised learning shines is anomaly detection. Here, the model learns the normal patterns in data and flags instances that deviate significantly from these patterns. This has wide-ranging applications, from detecting fraudulent credit card transactions and network intrusions to identifying manufacturing defects and strange phenomena in scientific data. Unsupervised learning is also a powerful tool for dimensionality reduction, the process of reducing the number of features in a dataset while retaining the most important information. Imagine you're working with a dataset of images, each represented by thousands of pixel values. Dimensionality reduction techniques like principal component analysis, PCA, and TSNE can help compress this high-dimensional data into a lower-dimensional space, making it easier to visualize and process. Some popular unsupervised learning algorithms include K-means clustering, a simple yet effective algorithm that partitions data into K clusters based on similarity. It's often used for customer segmentation, document clustering, and image compression. Hierarchical clustering. This algorithm builds a hierarchy of clusters, either by merging smaller clusters into larger ones, agglomerative approach, or by dividing larger clusters into smaller ones, divisive approach. It's useful when you want to explore data at different levels of granularity. DBSCAN, density-based spatial clustering of applications with noise. A powerful algorithm that groups together points that are closely packed, marking points in low-density regions as outliers. It's great for detecting anomalies and handling data with irregular shapes. Gaussian mixture models, a probabilistic approach that assumes the data is generated from a mixture of Gaussian distributions. It's often used for clustering and density estimation. What makes unsupervised learning exciting is its potential for discovering novel insights and patterns in data that we might not have even thought to look for. 3. Reinforcement learning. Last but not least, let's talk about reinforcement learning, a type of machine learning inspired by how humans and animals learn through interaction and feedback. In reinforcement learning, an intelligent agent learns by taking actions in an environment and receiving rewards or punishments based on those actions. The goal is to learn a strategy, called a policy, that maximizes the cumulative reward over time. Reinforcement learning is like training a pet dog. When the dog performs a desired action, like sitting on command, you reward it with a treat. When it misbehaves, you withhold the treat or scold it. Over time, the dog learns to associate certain actions with positive or negative outcomes and adjusts its behavior accordingly. This same principle is applied in reinforcement learning. The agent, like the dog, interacts with the environment, like the world around the dog, receiving feedback in the form of rewards, like treats. The agent's goal is to learn a policy that maximizes its cumulative reward over time. Let's consider a more technical example, training an AI agent to play a game like chess or Go. The environment is the game board, the agent's actions are the moves it makes, and the reward is based on whether the agent wins, loses, or draws the game. The agent starts off making random moves, but as it plays more games and receives feedback, it gradually learns to make better moves that increase its chances of winning. Reinforcement learning has been a game changer in many domains, including game playing. Reinforcement learning has been used to create AI agents that can master complex games like chess, Go, and Atari games, often surpassing human-level performance. Robotics. Robots can learn to perform tasks like grasping objects, navigating through environments, and even assembling products using reinforcement learning. Autonomous driving. Reinforcement learning can help train self-driving cars to navigate through traffic, handle unexpected situations, and optimize fuel efficiency. Resource management. In data centers and wireless networks, reinforcement learning can be used to optimize resource allocation, load balancing, and energy consumption. Some key concepts in reinforcement learning include agent, the learning entity that interacts with the environment. Environment, the world in which the agent operates and learns. State, the current situation of the agent in the environment. Action, a move the agent makes in the environment. Reward, feedback from the environment based on the agent's actions. A policy, the strategy the agent uses to make decisions. Popular reinforcement learning algorithms include Q-learning, SARSA, and policy gradients. These algorithms help the agent learn the optimal policy through trial and error by estimating the expected long-term reward of each action in each state. Real-world examples. To cement your understanding, let's explore a few more real-world examples of each type of machine learning. Supervised learning examples. Email spam detection. Train a model on labeled emails to classify new incoming emails as spam or not spam. Sentiment analysis. Predict the sentiment, positive, negative, or neutral, of customer reviews, social media posts, or news articles. Medical diagnosis. Train a model on patient data, symptoms, lab results, etc., to diagnose diseases like cancer, diabetes, or heart disease. Fraud detection. Identify fraudulent transactions based on historical transaction data labeled as fraudulent or legitimate. Unsupervised learning examples. Customer segmentation. Group customers into segments based on their purchasing behavior, demographics, and interests for targeted marketing. Anomaly detection in manufacturing. Identify defective products on an assembly line by detecting deviations from normal patterns. Topic modeling. Discover latent topics in a large collection of documents, like news articles or scientific papers. Recommender systems. Cluster users or items based on their similarities to provide personalized recommendations. Reinforcement learning examples. Autonomous vehicles. Train self-driving cars to navigate through complex environments while optimizing safety, efficiency, and passenger comfort. Trading algorithms. Develop AI agents that learn to make profitable trades in financial markets based on market conditions and feedback. Energy optimization. Optimize energy consumption in smart buildings by learning to control heating, cooling, and lighting based on occupancy and weather patterns. Robotics control. Train robots to perform complex tasks like grasping objects, navigating rough terrain, or assembling products through trial and error. Conclusion. In this lesson, we've taken a deep dive into the three main types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. We've seen how supervised learning leverages labeled data to train models for classification and regression tasks, using algorithms like decision trees, support vector machines, and neural networks. Unsupervised learning, on the other hand, discovers hidden patterns and structures in unlabeled data, with applications in clustering, anomaly detection, and dimensionality reduction. Finally, reinforcement learning trains agents to make sequential decisions in an environment to maximize a cumulative reward, with breakthroughs in game playing, robotics, and autonomous systems. Understanding these 3 types of machine learning is crucial for any software engineer venturing into the world of AI. It helps you frame problems correctly, choose the right algorithms, and develop intelligent applications that can learn from data. I hope this lesson has given you a solid foundation in the types of machine learning. See you in the next one.